Okay, so yeah, so we discussed this Witt algebra last lecture, right? So we have this. Let's recall from last lecture. I don't know what notation I used, but basically it had generators. We denoted them by Ln, and it goes minus infinity plus infinity integers, and they satisfy the relational bracket of Ln at n equal to n minus n and n plus n. Yeah. So this was the thing. And specifically, though, this was these mysterious type of relations came out from considering this derivations of the Laurent polynomial. So these derivations of this algebra C Z inverse. So we had this generators. Then in this picture, instead of working abstractly, defining something but generators and relations, we just define it by some specific operators acting on some vector space, and we just check that these relations are satisfied, and that's the way that relations actually was found to start with. No one would sit down and say that, hey, let's consider the algebra with these properties. It's totally insane. I mean, so Ln was minus z to the power n plus 1 e dz. Right? So these are like vector fields in the complex plane. And okay, so yeah, by the way, it's kind of fun actually. If you want to play with these things, you can just draw these vector fields for your fun in the plane. So, well, I mean, but what you have to do, you have to just write Ln is equal to minus x plus iy to the power n, and ddz, of course, is 1/2 ddx minus I ddy. So then you get two vector fields, you get two functions. You can separate this thing with the location in our Pn of x and y ddx plus Qn of x and y dy. I mean, you can take it, maybe just looking at, just for fun, you're looking at, say, n equal to -1, right? That's the simplest case where that power goes away, and we have just L minus 1 is equal to minus 1/2, right? Ddx minus I ddy. So that's equal to -1/2 ddx plus I over 2 dy, right? I mean, then this is just a constant vector field that pointing in the direction 1/2, 1/2, right? So this one would be something like this, right? And its length doesn't change. It's just that vector field. Is that right?
No. The arrows should all be pointing.
No, they should be all parallel. I'm sorry. Yeah. They should all be parallel. Yeah. It's just huh?
Left and up, I think.
Oh yeah. And then I just this also it should be all parallel and then left and up. Yeah. So this is like this. Yeah. Just get into nitty-gritty details of these vector fields. Then there is maybe one case n equal to I don't know, n equal to 0 if you want. L0 would be minus x plus iy ddx minus I dy, right? Let's see what we get here. And there's a half, of course. And so we get negative half of, so maybe I just put here 1/2. I mean, we get put ddx negative half of x ddx. What I've got here, negative half plus half plus I/2, basically yeah, I think so let's see. So what is the coefficient of, so let's not do it that way. Maybe what's the coefficient of ddx? We do get complex numbers, huh? Yeah. We get complex numbers in both of them. So it's a bit actually, so we get really like two vectors. Yeah, this is not a, yeah, this we don't get one vector, we get two vectors. So maybe it's not a good thing to try right now. So sorry, I'm just with these details right now doesn't matter for us. Yeah. So let me erase this now. Sorry. I wanted to give some mental picture. I mean but that's needs some more work, but that's okay. Okay. So what we want to do next, we want to extend this. So Virasoro algebra then is a central extension of maybe I call this Witt algebra W. W. So this V is equal to W, i.e. V is equal to W direction C, where we have a bracket. Okay, so I can just put maybe, so it's kind of C times C, where C is a central element. It's central, and bracket is defined by so the bracket of two elements here, like x and y here. So let me put it like this. So we just define bracket of some element here. So let's call it. So we need some notation. Say Ln plus Lm, say, plus C. Or maybe I just say A plus C and B plus C to be equal to the bracket of A and B plus basically I would put here something like C times omega of A and B. With omega That's not a very good notation, but I use it nevertheless. Omega from W cross W to C, a 2 cocycle. A V algebra 2 cocycle. V algebra 2 cocycle. So there are some stuff I have to define here. First of all, C central means that bracket of A and C is equal to 0 for all A belonging to W. We just want it to be central. You may ask why. I will explain why later on. That's a legit question, but I'll explain it a little later. But this is one of the conditions we want.
C has to be an actual element of the Witt algebra?
Yeah, so we added one more generator. We call it C. And so we defined commutation relations for this C with other elements in order to define the bracket. And where those commutation relations come from, it has to be explained. It's not obvious. So this whole business is called central extension. And I have to tell you why central extensions matter. That's I owe you this explanation. Okay, but so just defining terms, central means this. Now, this 2 cocycle, I have to define it, what it means. First of all, omega is C bilinear, just as it's a bilinear map. Bilinear plus is more than bilinear. It's also a 2 cocycle. So the Lie algebra 2 cocycle means the following thing: for any A, B, C belonging to W, for any A, B, C, 3 elements belonging to W, we have this relation that omega of bracket of AB and C plus omega of A and bracket of B and C I'm inclined to say this is equal to, but I'm not 100% sure. But that's something like this. No, actually, I need some more conditions. So it could be that I also need. No, I think that's okay. It's full cycle for the cohomology theory for Lie algebras. But for now, let's just take it as is and then see what we can do with it, and then I will verify this is correct. Okay, so by the way, where this condition comes from? This condition comes from the fact, we can check it actually, the fact that you want this new bracket to satisfy Jacobi identity. This just comes from that. Okay, so let me just write it here, and that will give us a way to verify whether this is correct or not. So the Jacobi identity for this thing B, we want this new bracket to satisfy this condition, bracket of A, B, C plus plus bracket of A and BC plus bracket of so we have to be very careful surrounding this thing. So I just want to keep this form and then circle this thing. Yeah, exactly. So this is going to be bracket of C, A, and B plus bracket of B, C, and A. Yes, so with this definition of bracket now, let's see if we can drive this condition among for the cocycle for this bilinear thing. This one. So let's check it just quickly. This bracket, according to what we know, is the usual bracket of AB. So this is, I just put it like this, AB old plus C times omega of AB, because this bracket is the new bracket, and it's given by this plus C times omega of AB. And we have got C, right? Plus circle equal to 0, these two terms. Right? So let's compute this now. What we get? What kind of term we get here? Okay. Well, I mean, then this one is a term like this, because we have got here bracket of AB old and C old plus omega of, right, bracket of AB old plus C omega of A and B, huh? And then I've got C, right? Then I've got C plus circulations equal to 0. But it should be 0. Okay, so let's see what kind of things. Okay, one of the things that I forgot to tell you about omega is that these cocycles, the algebra cocycles, always have to be skew symmetric. So this we impose the condition that they should be skew symmetric. So let's assume omega is skew symmetric. Okay, so what? How can we compute this term now? That bracket. And by the way, I guess that's just what kind of bracket I have here. So I computed this. Should I put an old here or no?
It isn't bracket, it's round bracket for field.
Sorry?
It's a round bracket.
Oh, this is actually, it's not a bracket. This is the round thing. Yeah, it's this. Sorry. Yeah. Thanks. Good. Okay, very good. So now let's compute this. What kind of things we get? First of all, I mean, well, this term is just there. So, now, so omega of bracket of AB and C over there.
Or linear should be, it should be omega over the, it's linear on the first.
But then there is something like 1 1 appears here. So but I think we made a mistake somewhere.
Maybe the other terms they cancel each other out. We have two other more.
We have two, yeah, we have those, but I want to work this out and then by cyclicity get this thing. But I think we
There's something going wrong with calling an element C and C being the special element of the central extension.
yeah.
Because I think the omega,
Oh, there is the
shouldn't
B
be
and
the first argument of the omega should
Yeah.
just be the commutator of A and B.
yeah. So it's better not to do it now.
I think I got it. I think what you want for the two co-cycle is just essentially the Jacobi identity, but the outer brackets become omegas.
Oh, so
So you want omega of bracket A, B, and C plus cyclic permutations to be 0.
oh, this one equal to 0.
I think that's what you get.
But we also need skew symmetry
Yeah.
plus skew symmetry.
I think essentially, because I think I've seen this before, and then my conclusion was you want omega to be essentially a bracket, but not quite. Because the bracket is skew symmetric and has Jacobi, and it's
Yeah.
bilinear, and omega is the same thing.
So now for me, okay, let me, if I may allow to waste 5 minutes, I would just try to derive it from very general definition. So, but then I have to know what kind of module we're considering. So this is a 2 co-cycle of A with coefficients in G again. Maybe acting by adjoint. Well, no, I'm not sure I can, because I don't know what the modular structure is. So, yeah. So, sorry about that. So I'm not prepared to derive the condition. If that's the case, then yeah. But we can consider it. But now the fact is that.
May I ask a question?
Yeah, sure.
Doesn't it always exist? Can we always find such skew symmetric?
No, I mean, of course, what happens is that 0 is always going to be something, giving you an answer. But that's not interesting. But basically, what happens in each case, you have to compute essentially that second cohomology and show that what's the dimension of that second Lie algebra cohomology. And in this case, what happens, this is the fact that I was going to write. What happens is that this cohomology that is of interest is essentially one-dimensional. So there's really one co-cycle up to obvious modifications, which are
it's non-zero. It's
up to co-boundary terms. Yeah. So let me just write it here. Fact up to some legal modification, whatever it means, I did not define it, sorry. What legal modifications means. There exists up to scale then a unique two co-cycle on Witt algebra. So this two co-cycle was discovered by Gelfand and Fuchs actually before Virasoro. So this is due to Gelfand and Fuchs. Maybe Virasoro also is important, but I'm not sure. Maybe Virasoro relevant here, but this Gelfand and Fuchs found this in their work on cohomology of vector fields and infinite dimensional Lie algebras. They had a celebrated work. They constructed also characteristic classes using cohomology of vector fields on manifolds. and formal vector fields. So let me tell you what this co-cycle is and how they wrote it, and then this language. Okay, so Van Hook's co-cycle, they wrote it like this. So imagine, so now. So they wrote it like this. So let's take f of z, dz now, right? This is one element of the Virasoro algebra where f is some Laurent polynomial, could be, and g of z, dz. Then they define omega of these two things. G dz. They define the omega to be given by this integral over S1. I believe f prime, g prime, double prime, g double prime, dz. So let me, yeah, I think that's the right formula. So here, to understand the integration, we just understand it in the sense of complex analysis, namely this integral equal to 0 for any k different from -1, and integral of zk, z minus 1 dz is 2 pi I. But because this is just a scale, for us this 2 pi I doesn't matter. We can define it even to be equal to 1 if you want. So this is the now what you need to check is that this is a 2 cocycle. So that's a good exercise. You have to work out what is the right definition of 2 cocycle, and then here is a very good example exercise. Check that is a 2 cocycle. Now, checking that this is unique is a lot of work. You have to compute the algebra cohomology, you have to develop the right tools, and that's what they did in some celebrated papers, 60s and 70s. Now, we can work this out in terms of LM and LN, actually. Because, so apply this to minus z n plus 1 dz and minus z, I mean maybe n plus 1 and n plus 1 dz. So ln and ln, right? So let's see what is omega of ln and ln. In other words, is basically m cubed minus m delta n plus n. This is yet another exercise. So in other words, the 2 cocycle is 0 unless they come in conjugate pairs, like L minus 2, L2, L minus 3, L3. Otherwise, this is 0. And it all follows from this, because you can easily compute the derivatives of these functions and put it there, and then you get this strange cubic term. This. So this is now the Virasoro algebra. So the structure of bracket on the Virasoro algebra now is turned out to be like this. Okay. Any question by them? So the core is that the bracket on B is given by bracket of M. Sorry, I'm just using bracket notation for all of them now. I don't put new or old or this sort of things. So this is the old bracket, which we know what it is, which is M minus N, Ln plus N, right? Plus this central term modified by this coefficient, plus C over 12. It turns out to be, maybe I'll just write it here, C over 12. There is this term, which is, I put here, sorry, M cubed minus M, delta N plus N. Let's see. Now, I have to explain. The C, as we agreed, is just a constant because this is up to a scale, nothing changes, right? So C is a central element. It's called central charge. Now, why is it called central charge? Maybe we have to go into conformal field theory and the quantum mechanics aspect of it to understand why this was called central charge. Hopefully we'll get there sometime, but this is just called central charge, and this 12 is convenient normalization. It's just a normalization. The rest I explained. This is the definition of bracket on the Virasoro algebra. So Virasoro algebra is a central extension of the Witt algebra. That's it. And we know that up to normal scale, there is a unique central extension. At least. Question?
Going back to the definition of this bracket, because the Virasoro algebra has an extra generator.
Yeah, which is C.
But is that the same C as the complex number C? Yeah, in the direction there?
Which one? This one?
Because with the C over 12 there.
Yeah, this C is an element of the Virasoro algebra.
Right.
And this is the omega.
Yeah, and C is still central in you.
Yeah, C is central.
So it doesn't matter.
Yeah, C is really central. Yeah, so it's kind of, the notation is a bit confusing here, but it's a powerful notation nevertheless. Does it make sense?
Yeah, I think it does make sense. What I was wondering is it obvious that there is an element in the center?
Oh, we just defined it to be like that.
Oh, so
yeah, you see.
Oh,
you remember,
I think I misspoke in my earlier question. I meant to ask, is C an element of the Witt algebra?
Oh no.
Right. Okay.
Now we define V equal to W direct sum, but I didn't put W direct sum C complex numbers. I put C. C
is just an abstract.
C is an abstract central.
Oh,
yeah. Cool. Yes. Very good question. So that's the Virasoro algebra, which is this. Okay. So I think the rest of today I'm going to justify this. Why this strange definition? Why we need central extensions? Why we need, and then maybe we can derive the condition for cycle condition there. But basically the real question is why we need this. I mean, why? Okay, so let me explain now. It can be explained. So first of all, maybe we quickly answer. So why we need Virasoro algebra? Because I said that for conformal field theory means that is a kind of field theory or quantum field theory that has this conformal group or conformal Lie algebra as its symmetry. And Witt is the infinitesimal symmetries of the complex plane in some sense. So, but why we extended this to this one-dimensional extra one dimension? The reason is that actually representations of symmetries in quantum mechanics and quantum field theory, they are really projective representations. They are not usual representations most of the time. So the answer is quantum mechanics needs projective representation, not usual representation, needs projective representations of Witt algebra. And so if I want to summarize everything in one sentence, I can say that projective representations of Witt algebra is the same as usual representations of Virasoro algebra. That's basically equal to representations of Witt algebra. That's the reason. That's the reason explained in one sentence. But now I have to unpack this sentence. Why this makes sense? Because if we believe in this, then okay. I mean, we have to look at representations of the Virasoro algebra, which is much more complicated than Witt algebra. So let's see. So let me explain now. So first of all, what is symmetry? I mean, sort of, there is a naive idea of symmetry in quantum mechanics. So naive, I emphasize this is kind of naive symmetries in quantum mechanics. So what is it? I mean, we have a unitary operator U from the Hilbert space to itself. Operators U from Hilbert space to itself, unitary. And what happens is that this unitary, it's a symmetry of the theory if it commutes with the Hamiltonian. U is a symmetry if U H equal to HU, where H is equal to Hamiltonian. This Hamiltonian. So Hamiltonian is the energy operator of the thing. And this kind of, when you gain a little bit of experience with these things, it sort of makes sense for you because, first of all, it's unitary, so it doesn't change the lengths and angles, nothing. It's the Hilbert space structure is preserved and also commutes with your Hamiltonian. So it's really this language of linear algebra, Hilbert space. Okay, but for now, this is. Okay. But the point, so let me give you an example, actually. let's take your Hilbert space to be L2 of R. And let's take a U of F over X equal to F of X minus T. T belongs to R. I mean, this is like translation, right? So this is the unitary operator, and if your Hamiltonian is translation invariant, it would commute with this thing. So this much, you know. All right, now, but the point is the following: that the states or pure states of a quantum system is not vectors in the Hilbert space or rays. So states, so let me put it like this: pure states of a quantum system the P of H is just a projective Hilbert space, which is just one-dimensional subspaces of H. Okay, so this is the set of one-dimensional subspaces of H. The set of all lines through the origin. It's called the projective space of H. And of course, there is some structure here. It's not totally without any extra structure. It's not just a projective space, because Hilbert space has an inner product. And this inner product defines some sort of function on H, which is called overlap function, which we define it like this. So omega of some line L1 and another line L2, we can just define to be inner product of L1 and L2 divided by equal to L1 and L2 for any L1 belonging to L1 for any L2 belonging to L2. Of course, it should be different. And you can easily check that this function is independent of the choice of these vectors that you choose on those lines. So this function is called the overlap function or prime correlation, or I don't know, some maybe also called complex amplitude or something. This has different names in quantum mechanics. It's an important quantity, and it exists on this Hilbert space, on this projective space. Okay, so then what can we say? What is the symmetry of a quantum system now, according to this definition? According to this idea of the states, right? What should be symmetry? Because before we said symmetries are transformations of the vectors of the Hilbert space to itself that preserve the inner product. And then, of course, that commuting with Hamiltonian, that's for dynamics. But kinematically, it's just that one. But in view of this, we should define symmetry to be a one-to-one onto map from pH to itself that preserves this quantity. So that's the right notion of symmetry. So the definition then, the symmetry is a one-one onto map T from P of H to P of H such that omega of P of L1 and P of L2, T of L1 equal to omega of L1 and L2 for all L1 and L2. It means that it's rotating the lines or pure states in your projective space in such a way that the overlap or this amplitude function is preserved. Okay. So now the question is, where such things come from? How can we construct such things? It looks complicated. Well, there is an obvious way to do these things. To start with this original thing, because any unitary or linear map gives you a map on the projective space also. So that's simple. So let's get it then from there. So if for any u from H to H, this gives you a T from PH to PH. Oh, this has to be Hilbert space. Sorry. So, I mean, you can define it like this T of L to be equal to U of L, where L belongs to L, and this is different. I mean, if you have a map that rotates vectors, of course it rotates lines. I mean, sends one-dimensional subspaces to one-dimensional subspaces. That's just obvious from linear algebra. And it satisfies this condition when if the guy is unitary. And T satisfies. So let's call it a star. If U is unitary. So we have at least one source of quantum symmetries in this more general sense. But that's not the only one. Can you think of whatever coming up?
Don't have one yet.
No, it's not obvious. It's not obvious. No, it's not obvious. It's not a fair question. I understand. But so let's consider anti-unitary things now. So here is easy. That U from H to H anti-unitary. So what is anti-unitary? Anti-unitary means that first of all it's anti-linear, right? Plus there is this condition that it essentially preserves the inner product, but by conjugation. So basically, inner product of U of X and U of Y is equal to complex conjugate of inner product of X and Y. So this would be X, Y. So obviously, anti-unitary also induces a map on PH. From U, I think you can get a T from PH. You can check that. That's so let me give you an example of an anti-unitary map, which is
Does it preserve the overlap function though?
the overlap function.
It seems that we also conjugate the overlap.
Yeah, we conjugate the overlap function. That's true. Maybe I should modify my overlap function to take absolute value then.
Yeah.
Maybe I should modify it. Maybe I should take, because yeah, I think I should modify that to take absolute value.
Because we really want it to be sort of an angle, I guess.
Yeah, but the thing, That's kind of angle, right? But the thing is, in the complex space, angle between these complex lines, maybe.
Yeah, I think that's why you might take that value.
Yeah.
Because if the inner product is a complex number, angle becomes.
Yeah, becomes. It's not an angle notation. Yeah, I mean an angle intuition there. Yeah. Yeah, maybe you should take that. Yeah. Yeah. That's right. So indeed. So let's look at one example. U from Cn to Cn, you can take U, obviously, that's one thing you can do. You can just complex conjugate these things. But there is one even kind of more interesting example that it's related to charge conjugation and stuff, which is this one. U from C2 to C2, U of Z1, so Z2 is basically equal to Z1 bar, Z2 bar, there is I times sigma Y. So this is in Wikipedia. I also checked in Wikipedia. This gives this example. Sigma Y is equal to the Pauli spin matrix, which is second spin matrix, which is 0 minus I. Yeah, it's minus I. Yeah, you see, if we didn't put, okay, so if we didn't put this sigma Y, this would be the first example. But in that case, U squared is equal to 1. But for some reason, sometimes you want not only U to be anti-linear, you want U squared to be minus 1 also. That's also a feature. But in this case, you can check that for this one, U squared is equal to minus 1 in there. I believe this is related to this charge conjugation of Dirac and also this stuff that you're doing in the spectral algebra. Anyway, this is a side remark. That's not essential. What is essential is this. Okay, so we have two big sources of symmetries in this generalized sense of quantum systems. And the question is there anything else? So this was a big theorem that was proved by Wigner that there is nothing else. Any symmetry either comes from unitary or anti-unitary. And this is completely elementary statement. You can give it to students of linear algebra. Even for C2, the proof is not easy. Although, I mean, the statement is very elementary. And so let me write it now. So that's kind of very interesting. So this is the theorem Wigner. So around 1930s, I think, very early on in this, that any symmetry of the quantum system comes from either a unitary or an anti-unitary. So that's something that we need in order to justify that idea of central extensions now. So let's go back to, so now let's give me a group. So now, what is a group of symmetries of a quantum system? Well, it's just a projective representation of so symmetry of a quantum system is a projective unitary rep of G. Or, I mean, for some G, right? There's some group, it could be Lie group, it could be discrete group, it could be finite, infinite, doesn't matter. We say that G is a group of symmetries of the quantum system if you have a projective unitary representation of it, right? I mean, well, okay, now let's focus on unitary. So by Wigner, we know that each of those guys, so let's look at phi of G. So for each G, phi of G comes from, P of H to P of H, right? For any G. So now we can actually, so let's call it pi tilde. We can actually, Wigner says that this comes from either a unitary or anti-unitary. Let's assume we are in the case that it comes from a unitary. So Wigner shows that, so there exists pi G from H to H. So let's assume we are working with the unitary, restricting our attention to the unitary part. Unitary or anti-unitary, which we don't care for now. That induces pi tilde, right? Maybe I'll call it pi bar because that's kind of reduction. Yeah. Okay, now this being a representation means what? Means that pi bar of G1, G2 must be equal to pi bar of G1, pi bar of G2. Right? This is the idea of representation. It should be that this obvious representation condition set. Now, in terms of, so imagine for each G you have picked this pi G. Now the question is, what is the relation between pi of G1, G2 and pi G1, pi G2? So what is the relation between these two things? We cannot say necessarily they are equal, or we don't have to assume they are equal. All we can say is that this should be equal to some omega of G1, G2, so omega of G1, G2. Well, what is this omega? Omega is a map from G cross G to C. It's just a scalar. Why? This is a function of two variables. And in fact, it should go into U1 if we want this to preserve the that angle. Okay, so that's the thing, right? Now, there are several things, whether this lifting or choice of this pi G can be done in a continuous manner or not for all G in a uniform manner, and whether this omega is a continuous or measurable or a smooth function or not, that's an issue. But we can, we just bypass those issues. We just look at algebra right now. Just from the point of view of algebra, such relations should be satisfied. And then you have such things, you say that this is more or less saying that you have a projective representation. It's an alternative way of talking about projective representation. Okay, so the projective, mean, projective unitary representation can be alternatively defined as a map pi from G to unitary operators on H that satisfies this condition. Obviously, for associativity consideration, this omega has to satisfy some conditions, which would be co-cycle for groups in this case, not the algebra. And then you differentiate those relations, you get for Lie algebra, get the things for the algebra. Okay, so now central extensions. Because so far we talked about Lie algebra, but we can also talk about groups or groups. So what is a central? So for any group G, we can define a new group. Let's call it G hat, which is G for C. We can define a new product, G and lambda D prime, lambda prime, to be of the following form. This is basically GG prime. The second component is omega of G prime plus lambda prime. So this is an idea of central extension for groups. Obviously, omega has to satisfy this co-cycle condition that I don't derive it now, but you can find it in there. So what happens is that the projective representations in this sense are the same as representations of the central extensions of central extension. So this is a maybe lemma you can prove. Fixing this 2 co-cycle omega. There exists then a 1-1 correspondence between projective representation perhaps satisfying star and reps of the central extension. Of the central extension, which is defined by this one.
Star is the.
Oh, star is this. Sorry. I mean, this can be done in a more elegant way, even in terms of if you don't fix this omega, we can also talk about homologies of groups, but that's it's not very possible. So that's. So that's why central extensions are important in physics, because quantum mechanics, pure states in quantum mechanics are just one-dimensional subspaces, not vectors. And because of Wigner's theorem that tells us how to get from a naive representations to representation of pure states in a more elaborate sense. And the rest is just algebra. Now, we did it in this case for groups, but there is a whole theory you can develop for Lie algebras. You can say there's a quantum system has a Lie algebra of symmetries, and then you can go through this and then basically construct So that's why we have to look at central extensions of Virasoro algebra. Sorry, of Witt algebra, which is the Virasoro algebra. And if you give me 1 minute or 2 minutes, I can give you one example that you can actually see where this omega actually how this appears. Yes. Many examples. Any questions? Well, let me give you one example. Yeah. So let's take G to be equal to real line. And let's take H to be L2 of R. So let's define some representations here. U from G to unitary operators on L2 of R. So, well, I mean, so U of P over F acting on X, which is translation, right? This is just a translation. Obviously, this is the unitary transformation. Let's define another one, which is B. I mean, this is from R actually. So B from R to unitary operators on L2 of R again. V of some S on F acting on X is e to the 2 pi I S X F of T. Oh, sorry, F of X. So this is like a phase shift operation. That the first one is translation, this one is phase shift. You know what is the relation between them? I will write down the commutation relation, but I mean, what is the nature of this V? Its relation to U? Yeah, I meant some other also relation. That's also.
The Fourier transform.
Yeah, it's really like if you go to Fourier transform F into Fourier and want to know how this has to be done in the Fourier mode, you have to use this.
But should there be an X in the face in that case?
I put an X here. Oh, you mean there should be an X? It's the 2 pi I S X. Oh, you mean there shouldn't be?
If you translate by S, the Fourier coefficients rotate by e to the 2 pi I S.
Just that?
I think so.
Yeah. So then that's not Fourier, yeah. Yeah, this is a bit okay. So what I want to use, so maybe this will shed light on that. What I want to use this U and V for, not just for R, I want now to use them to define possibly a projective representation of R2. Because these are representative. But by the way, I mean, you agree that this is also representation. Because we just multiply. I mean, if you just do, you know, I mean, I'm saying V of S1 plus S2 Is it equal to B over S1, B over S2? Maybe not. Is it? So. Yeah, it is okay. I'm
pretty sure.
Okay, so that's good. Okay, so I mean, for the first one, of course, is obvious, even more obvious for you. Yeah. Okay. Good. Now I want to define some representation. Maybe I call it T from R2 to again U of L2 of R. So T of T and S acting on F. Oh, I just write it like this: T of T and S equal to T. Yes. Yeah, I mean, this is a proposal. But you see, this is not going to work because, I mean, the only way for this to work, to be a representation, is that these two operators commute. Okay, so we just say that since UP Vs is different from Vs, UT, this T is not a representation. T, is not a rep. I mean, indeed, I mean, to see that, because we can just say, if it was a representation, just you see T and S, we would write T0 and S plus T of T and 0, and you would go with each of them, and then you would draw the necessary condition. But it should be like that, but it is not. Okay, so, but let's see what's the difference, I mean, in this case. So basically, what I'm going to claim is that T of alpha plus beta is equal to omega of alpha and beta, T alpha, T beta, where alpha and beta belongs to alpha. So we have to compute this omega now. What is omega? Well, I mean, let's compute this one. So this is basically so this is like TS. So alpha equal to TS, beta is equal to, maybe I just put alpha and alpha prime. Alpha and alpha prime. T alpha, alpha prime. Alpha is equal to TS, but alpha prime is equal to T prime, S prime. So this is T of, again, some boring calculation, T plus T prime and S plus S prime. So this is going to take a long time, I think, to compute this, but I think it can be shown that in fact such a thing exists. So this defines a projective representation in this case. Yeah. And we get a projective representation. Central extension in this case, actually, of R2 in this case is a very interesting group. So let me write it, how that we have come this far. So some calculation obviously has to be done in this case. I don't want to do it here because it just takes too long. But the central extension of R2 with respect to this omega, so it's going to be like R2 direct sum some, we can put, so now I'm going to put some H instead of C. HC turns out to be actually the Heisenberg group, famous Heisenberg. So what is this Heisenberg group? Be careful. Yeah, so no, I think that's okay. So the Heisenberg group is this. So H3 is 1 X H 0 1 Y 0 0 1. X and Y belonging to R2. H belong, oh sorry, X, Y, H belong to R. I'm a bit, maybe I just like let me define the group structure. It's just a matrix multiplication. Question?
Yeah, I'm confused about the C versus R.
Yeah. Oh, yeah, sorry. R, yeah. Yeah, because Heisenberg group actually exists over all fields or rings even. We can, but I mean, in this case, yeah, that's a good point. Okay, so now what is the let's look at multiplication here. So, I mean, you agree that these things under matrix multiplication form a group. So it's a three-dimensional Lie group. It's and actually, as a topological space, it's isomorphic to R3, three-dimensional Euclidean space. With this. So let's look at what happens to XY part, which here was TNS. So if you have 1 X H 0 1 Y 0 0 1 times again 1 X prime H prime 0 1 Y prime 0 0 1. What do we get? We have 1 here. We have got what do we get? We get 1 times, so we get X plus X prime. Yeah, that's what I want. And there is some stuff here, which I don't write. And then I've got 0, or I'm going out of the thing, so I should not go there. So let me continue here. So sorry, 1 X plus X prime, and some stuff there, which I don't write. And then we have got 0 and 1. And here, though, you see 3 given by prime plus y. And then I've got 0, 0. This is the part that is the group cocycle appears in this case. This is the part. But you see, this R2 is there. In other words, we have R2 embedded in H3, and the quotient is R, and it's 0 here, and here is. So there is this central extension. Oh, no, bad, my bad, sorry. This is 0 R H3 to R2, and here's this R, this copy of R, which is over there, is in the center. You can check it. That's in the center. This is the group itself, Heisenberg group, and the quotient is R2. The quotient map is just the map that you take a matrix, send it to this above diagonal components. So representations of these Heisenberg groups are basically projective representations of R2. So the corollary is basically now so projective reps of R2 is the same as reps of H3 of Heisenberg.
Unless maybe R2 has more extensions, more central extensions.
Yes, that's a very good comment. Yes, there aren't. But up to these trivial modifications or co-boundary terms, adding co-boundary, there are. Yeah, that's right. So that's how. Yeah, I mean. Okay, so I have given you one representation of the Heisenberg group, which is coming from that UT and VS business. And that's the exponential of the Schrödinger representation of quantum mechanics, basically. And then there is a very big theorem called Stone von Neumann theorem that says that up to some trivial modifications, that's the only one in the dimensional irreducible representation. So that's a big theorem that it takes maybe a few lectures. Stone von Neumann theorem, but that's not what we are going to. Okay, so yeah, everywhere you go, you meet this interesting theme. So maybe I should just pause.